So we will only do here revision of electricity. We will not go in much detail. So first of all, current. The formula of electric current is dq by dt. Let's say there is any cross section, there is a wire here and there is a cross section of this wire chosen here. Then let's say there is a cross section of wire chosen here. Then the amount of charge passing through it per unit time. The amount of charge passing through this cross section area per unit time, that is called current. I is equal to the dq charge which is passed through it in dt time. That is the current passing through this area of cross section. And if we go to the microscopic level, we will get another formula for I. The formula for I is NEA Vd, where Vd is the drift velocity of electron. So current formula is NEA Vd, and if the relation of charge and T is given, then we can find by dq by dt also. And if we know the number density of electron, N denotes the number of electrons per unit volume, and it is in units per meter cube. The volume unit is meter cube, and is the electrons charge, which is electrons charge is 1.6 into 10 to power minus 19 coulomb, and is the area of cross section of wire. Let's say this is the wire and it has current flowing in this direction. This is I current flowing in this direction. Then the area of cross section is this. This area of cross section of the wire would be equal to A, and V is the drift velocity of the electron. Drift velocity is the average velocity, sorry, we can say average speed of electron. This is the average speed of electron which contributes to current flow, which contributes to the current flow. So all the part, and in case of any conductor given, the drift velocity is very small, like 1 centimeter per hour, like this. The speed of the electron in the medium is very small, and even though the speed of electrons in this medium is very small, the signal travels very fast in this wire. There is something called electric signal of electricity signal and its speed, and there is another thing, the speed of electrons or charge. In case of, let's say there is a battery here provided with a potential V, then the electron, let's say moving in this direction, from negative to positive. Let's say there are some electrons in this. So this electron moves little bit in this direction, and as they become closer, this will feel more repulsion from this, and it will move in this direction, and this will move little bit in this direction, and this will similarly move little bit in this direction, and this will move little bit in this direction, and this also shifts little bit, and this also shifts little bit. And all this happens very quickly. This happens at very large speed, like 25% of speed of light, or 55% speed of light, or 75, something like that. The speed of this signal is very large, means the signal means the displacement seen at this position is it happens very fast. Means if I take a very long wire, and I add a bulb here, I am adding a bulb here, then what happens is that the electrons don't, okay, when I turn on the switch, let's say there is a switch here, and I close it, then suddenly what happens that the electron at here will push the electron at here, it will push the electron at here, and it will start pushing the electrons here, and it will travel with very large speed. This signal travels with very large speed, and the bulb will glow quickly. Like if I if I close the switch just now, then just in a few milliseconds this bulb will start glowing. Or if this is an LED, let's say there is an LED light, this will start glowing in just a milliseconds, and this happens very quickly even though this length is very large, and the electrons are moving at the speed of like 1 centimeter per hour, or very small, while this length is meters, 10 meter, 20 meter, or 100 meter. While the electrons cannot reach at this position even in a day, but the signal reaches from this point to this point in just a milliseconds. And this is because we don't actually need this electron to reach here for the current to flow in this LED. For the current to flow, there are already some electrons at this place. There are already current electrons present at this place, so I just need to move them, and as it starts moving, this causes a force acting on this all electrons, and this also starts moving. So as it starts moving, these also start moving. So, and the time taken for the motion to appear here after this electron starts moving at here, this is, let's say, time taken is t and the length is l, then the speed of signal will be l by t, and this is very large speed, like not the speed of light but approximately half or some percent of it. It depends on the material of the wire used. While the electrons are moving very slowly in the wire, they will rarely travel like 2.5 centimeter or 6 centimeter in an hour. And this is the formula for current, and there is another formula for current, which is V by R. In Ohm's law we get V is equal to Ri. If we know the resistance, then we can also calculate the current by knowing the potential difference. And there is formula for drift velocity Vd, which is equal to minus E tau over m, where m is the mass of an electron, E is the magnitude of charge on an electron, E is the electric field present. Means, let's say there is a wire, and in this wire there is some electric field present, E, and then the electrons will have some drift velocity in this medium in the same direction as electrons will have drift velocity in the opposite direction, because there is a negative sign. As you can see, the electrons will start moving in the opposite direction with the drift velocity Vd, and this is the average velocity, and is the electric field present in the conductor, and tau, it is the average time between two collisions. There are, let's say, many electrons present in this medium. Some will collide after t1 time, some will collide after t2 time, some will after t3 time or t4. So they collide after different times. Means that time between two successive collisions can be different for different electrons at different instants, and taking the average or mean value of all this time between two successive collisions, the average value we get is this tau. So tau is the, let's say, t is the time between two collisions of any electron, then it is the time between two collisions for an ith electron. So taking the average of all these electrons, we get the average time between two collisions, which is tau. and this is the formula of drift velocity. Now there is another term which is mobility, which is the property of the conductor. So what happens is that we know that E is constant, E is a charge of electron, M is mass of electron, which is constant. These two are constant values for any type of material, any situation, and E is dependent on the external field, which is an external effect, and tau is the property of medium, and also depends on a little bit electric field. Vd, which is directly proportional to the electric field. Now the drift velocity per unit electric field, which is E tau over m, this is called mobility, means the drift velocity produced per unit electric field, that is called the mobility. This is the mobility. It is the property of a conductor, and the tau is almost constant for a given conductor. Vdy is the mobility. Now if I know the mobility in a conductor and electric field is given, then I can tell the drift velocity of electrons. This is the mobility of electrons. It can be written as mu e, mobility of electrons, because this is the velocity of electrons. The velocity electron gains divided by the electric field which causes them. Now the next thing, resistance, Ohm's law. In Ohm's law we have V is equal to IR. This is the basic thing we have studied in 10th class, and the resistance is given by rho L by A, where rho is the resistivity of the material, or we can say, let's say there is a point here A and this is B. There is some resistance present between these two points, and I want to find the resistance between A and B. Then it would be equal to this, let's say this is a conductor, this is a system of conductor of some, I can take a effective resistivity and some effective length and some effective area of cross section, then I will get the value of resistance. Let's say there is a conductor with varying area of cross section but constant resistivity. So I can simply take small elements, I can divide this conductor in small elements, and it would be of dx length, and the area of cross section would be related to the distance, let's say from this, and their distance is x. So this total length is, let's say, L, and the resistivity is R. So I can say that resistivity is the integration of these small elements resistance from this point to this point. The resistance between these 2 points is dr, then resistivity, summation of all these resistance values of these elements will give the total resistance between this point and this point, which is rho, which is constant, and 2 dx over area of cross section integrated from 0 to L. The area can be dependent on dx, it can be dependent on the x, so it can be a function of, area can be a function of x. So this is how we can integrate and get the value of resistance. We just need to do some integration in case of parallel. In case of, let's say, materials, there is a, let's say there is a one end here A, there is one end here B, and it contains some materials of resistivity varying along this direction. So I can take a small element here and assume that it has resistivity rho, and I have to take the parallel sum of all this resistance, let's say all this L length. So I will get the 1 over R AB is equal to the summation of the sum of resistors in parallel is the will give will be given by the resistance of this small part, a small element, which is dr. Sum of reciprocals of all these resistors will give the reciprocal of this net resistance between them, which is rho L by dA. This is dA area. Taking the 0 from 0 to A, let's say total area is A. So taking from 0 to A, I can calculate the total value of resistance between, effective value of resistance between AB, where L is constant for all. Now the resistivity, in case of the resistivity formula we have derived is, the resistivity is given by mass of electron divided by n square tau, and the resistivity is also called reciprocal of conductivity. This is conductivity. So it can be understood by, the heavier is the mass of electron, the lesser it will move, the slower it will move. So the slower electron will move, the lesser will be the current. It means resistance increases when mass increases of electron, and the more is the charge of electron, the more is the force on the electron, and hence there will be larger speed of the electron, which means current would be large. So the charge of electron, if it increases, the current increases, means resistance, we can say resistance is decreasing. So that's why electron is inversely proportional, charge is inversely proportional to, we can calculate the value and we will get that charge square, the charge of electron square is inversely proportional to the resistivity. This comes from this square value comes from some calculations, derivations, and if there is more time gap between the collisions, the electron will give a high velocity because it is constantly accelerating. The more time we will give, the more velocity it will gain, so it will travel with a larger speed. So if it moves with larger speed, again the current will increase, means larger tau means smaller resistivity. So that's why it is also inversely proportional. And eta, which is the number of electrons, the more is the number of electrons present per unit volume, the more current can follow. So that's why it is also inversely proportional to resistivity. That's how we can understand this formula. Now there is one term called current density, which is a vector quantity. Since current is not taken as a vector quantity, we need any other vector which can help in using the current with a direction. So the current density has the same direction as current. One thing I would say here, when there is a conductor and there is some electric field in this medium here, let's say electric field is in this direction, then the current will also flow parallel to this electric field. So the direction of electric field, direction of current equal direction of electric field at any point, at any position. At any position, the direction of current is the direction of electric field, and this is also the direction of current density. So we have the formula of current density vector, which is equal to sigma n2e, and there is formula for current passing through any area, which is j dot a vector. This is the most correct formula. Let's say the density of current I will represent it by, let's say, some lines. Let's say this is one charge passing through it, second charge, third, fourth charge. Let's say there are some electrons passing through this region, and this is the density of them. And if I take a cross section like this, Then if I place it here, then 3 electrons are passing through it. The time taken by them is to pass through this point is same, and if I tilt this area at this angle, then only 2 electrons are passing through it. So this reduces the angle, reduces the number of charge passing through this area, which thereby reduces the current passing through it. Current is simply the amount of charge passing through the cross section per unit time. So this will be dependent on the angle between J and A. And how to define J? Current density. Current density, as we can see here, it is JA cos theta, where A is the area vector. And to tell the current density J, we need to write the current passing through a small area element. Let's say there is a small area element dA, and the current passing through it is I. Then I will have to take the component of the area that is perpendicular to this current. Means, let's say there is a small area of cross section dA like this, and the current is flowing in this direction. This is current flowing in this direction. dI current is flowing in this direction. Now to tell the current here, current density here, I will have to take the perpendicular component of the area, which means, let's say they make theta angle here, then I will have to take the dA perpendicular, this is area perpendicular to current. This is dA area. dA areas project. This is area perpendicular to the current dI, and so this formula will become dI over dA cos theta. Similarly, we can use this, that I over A cos theta is J. So we have to take the area which is perpendicular to the, we have to take the component of the area which is perpendicular to the current vector. Note, we don't take the component of area, current, but the area only. We have to be careful to take the component of area only, not the current. The current and the current density is in the same direction as the current. Let's say the current is flowing in this direction, then current density will also be in this direction. As we said here, they all have the same directions. Now moving ahead, R is equal to, in case of metals or some alloys, we see that the resistance is variable with temperature. In case of alloys, we see that the resistance increases linearly in some alloys, not all. In case of some alloys, the resistivity of the material increases with temperature linearly, and when there is 0 Kelvin, this temperature is in Kelvin scale. When the temperature is absolute 0 Kelvin, then there is some finite resistance of a metal. If there is a metal or alloy, then there would be some finite resistance at 0 Kelvin. There would be some resistivity, and with increase in temperature, the resistivity almost linearly increases, approximately linearly increases. This is a graph shown by nichrome wire. Nichrome. And in case of normal metals like copper or any other metal, the graph looks like this. It increases in a some kind of parabolic manner, like some degree of temperature T. Rho is some, okay, we don't go in detail. The graph looks like this for any normal metals. And for semiconductors, we know that the formula of resistivity is mass of electron over n e square tau, which can be written as m upon e square into 1 upon n tau. Now what happens is that this is a constant value. Now when I change the temperature, n doesn't change in case of metal. In metals, all electrons are free electrons, which are causing the current. And when I increase the temperature, the time between collisions also decreases, because they gain higher velocity, and since they gain higher velocity, they collide more quickly. So the time between collisions decreases as the temperature increases. So temperature increases means tau decreases in case of metals. It is true in case of any other body. For all it is true. For all materials it is true. Now what happens? This is a constant value this is approximately constant for metals, because almost all the electrons are free to move, which are already moving. And so when I increase the temperature, this value decreases, causing the resistivity value to increase. And in case of semiconductors, not all electrons in the medium are free to move. They need some energy to start contributing to the current. In case of, let's say, semiconductor, there are some free electrons which are providing the current. And when we increase the temperature, some more electrons will get produced, which will increase the number density of this, it will increase the number density of electrons. And increasing the temperature will also decrease the collision time, but the increase in density is much more than the decrease in temperature. So this is increased much more, that it dominates this tau. So this will increase, and therefore the resistivity will decrease. So in case of semiconductor, the resistivity decreases. Now for alloys, we can, or for some metals, for a small range of temperature, we can say that for alloys or for a normal metal, for a small range of temperature, we can say that the resistivity changes linearly with temperature. Means resistivity can be written as mt plus c, where m is slope of this line and c is some constant. So resistivity can be written like this. And for this small range, we can use this relation, and we will derive the relation for the change in resistivity, that resistivity is equal to rho naught, resistivity naught, plus 1 into alpha delta T, where alpha is the temperature coefficient of resistivity, and this is the change in temperature, and rho naught is the resistivity. We can write this equation more properly as rho naught bracket 1 plus alpha bracket T minus T naught, where rho naught and T naught are the reference. These are the reference resistivity and temperature. Let's say at T naught temperature, the resistivity is rho naught, and these are the reference temperature and resistivity. both occur at the same instant, and generally the T naught is generally taken at 0 degree Celsius, and same therefore the rho naught is also at 0 degree Celsius. So the rho naught taken is also at 0 degree Celsius in general. But if given in the equation that the T naught is at some, let's say, any x degree Celsius and rho naught is at same x degree Celsius, then we have to take that as a reference temperature here. But in general this is 0 degree Celsius, at 0 degree Celsius, and we have to put the value of this reference value. Now the value of alpha is very small in case of metals, and going ahead, how to read the resistance code. Let's say we have seen that there are resistors like this, they look like this, and they have some color strips here which are called color codes. There are four strips of color, and the first three strip tells the resistance value. This tells the value of resistance in ohm, and this tells error. This is called tolerance. This error is called tolerance. And this resistance is given by a method where the first color gives the first digit. This gives the first digit. This gives the second digit, and this third code gives multiplier. This is the multiplier. So we'll write the number. Let's say this is the first digit, let's say x, this is y, and this is a multiplier. So it is like x y digit multiplied by some multiplier, let's say m. This becomes a resistance, and this tolerance is given as percentage of error. And the color codes are having values VB. We will go in the reverse order. V, B, G, Y, O, R, pure, and then white and gray color. Where this is black, this is brown. Black means 0, brown means 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is white. White has 9, blue has 6, red has 2, and black has 0. We need to be careful. And now there are colors called gold and silver. Gold color is not used for first or second. Gold and silver are not used for first and second strip, but it is used for third and fourth. These are used for third and fourth strip, means these two helps in telling the multiplier value and also the tolerance. So when it tells the multiplier, it is 10 to the power minus 1, and when silver is used, it means 10 to the power minus 2, and when it gives the tolerance value, then in case of gold it is 5%, and when silver is used, it means 10% error. And when there is, sometimes in some resistors there is no strip here, this is called no color. when there is no strip here, means no color, then it only tells this only tells tolerance only. This doesn't tell any of these. This tells tolerance and it is of 10% error. If there is no color here, then it means 10% error. It can be confusing to know which side is no color. Let's say there is no color, then we may get confused from which side we should start. We should start from this side or this side. It can be confusing when the no color is given. But if colors like gold, silver or any of these is given, gold or silver is given, then it would be easy to. But if for error there is gold or silver used like this for these tolerance values, then we can easily say that we have to read like this. This is the first digit, second, this is the multiplier, and if this is gold and silver gives tolerance. And this is for the digit, this is the digit for first and second. And in case of multiplier, these are used for multiplier also. It means 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4, dot dot dot, so on. All these color are used for multiplier also, and these are not used for tolerance. Gold, silver and no color is used for tolerance. Gold, silver and all these are used for multiplier, and only these are used for color codes. Gold, silver are not used for resistance values, means first and second digit is given by only these, and multiplier is given by all these, and tolerance is given by this and this. Now let's take an example to understand how to read the color code. Let's say this is gold, this is green, this is white, and this is red. Then the value of resistance we will read. Since this is tolerance, then first we will have to read like this. This cannot give the first digit because it is for tolerance and multiplier only. So red means 2, gray, this is green, which means 5, first digit, second digit, and white is a multiplier. This third strip is a multiplier, so white has value 9, so 10 to the power 9, 10 to the power 9. This is the value of resistance, and the percentage error of resistance is equal to 5% for gold. Gold has 5% error, so I can write the resistance more correctly as 5% is 1 over 20 part of this, which means 2.5 into 10 to the power 10 plus minus 120 part of this, which is 2.5 upon 2 into 10 to the power 9. This would be the resistance value of this resistor, where the resistance value can fluctuate little bit. Now next thing, this is simply that the current cannot accumulate, so the I current in a circuit, let's say this is position 1, this is cross section 2, then the area of this cross section is, let's say, A1 and this is A2. Then since the current at here is I1 and there is I2, I1 should be equal to I2, which means J1 dot A1 should be equal to J2 dot A2. So the total current, which is given by this current density into area vector, this will give the total current. The more is the current density, the lesser is the area of cross section, or the more is the cross section area, the lesser is the current density. It behaves like the flow of water. Let's say there is water flowing in this shape. If water is flowing from this side, it is moving with a high, let's say this is moving with a slow speed v. the area decreases and the speed increases. Similarly, in case of current, if area is high, the current density is, let's say, J1, and the area decreases, so the current density J2 here would be greater than J1 because area is decreased, so current will flow with more density, but the current magnitude will be same everywhere. Now calculation of resistance. First, for resistance calculation, when combination of resistors if we have parallel combination of resistors, then we have 1 upon, let's say there is a point A here, B here, and there are resistors added parallelly like this, dot dot dot. This is Rn, this is R1, this is R2, this is R3, and this is Rn. Then all these are parallelly connected. Then the effective resistance between RA to B, let's call it R effective, then it will be given as 1 upon R effective, which is equal to the sum of reciprocals of all resistance dot 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 to the Rn. And in case of series connection, if there is a series of resistors connected in series, let's say this is a one end and there are resistors dot dot dot, this is B point end, and this is of R1 resistance, this is R2 resistance dot dot dot, this is Rn resistance. So if they are connected in series, then the resistance between RAB, let's call it R effective, then the resistance between RAB, which is R effective, will be given by R1 plus R2 dot 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 plus Rn. So it is the sum of all resistance, it is a reciprocal of the sum of all reciprocals, that's it. Now in case of capacitance, in parallel case, the capacitance effective is given by C1 plus C2 plus C3 dot dot dot, and in case of series, the C effective is given by C effective is equal to 1 upon C1 plus 1 upon C2 plus dot 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 for capacitors. Now the next topic is combination of cells. Combination of cells can be of two types. Let's say first is can be of three ways. One is series, one is parallel, and the third can be mixed. So we have, let's say first series combination. In series combination, let's say there is a cell here, one cell is here, there is one cell here. I am representing it by a box for right now. I will tell you later why. Let's say one cell is placed here, one cell is placed here, one cell is placed here. This is end A, and dot dot dot. This is the last cell here. This is the end B. This cell has EMF E1 and internal resistance R1. It has E2 EMF and R2 internal resistance, so on dot dot dot. This is EN and R and internal resistance like this. There are cells connected like this. Here EMF, what does EMF mean? EMF means when the battery, there is some battery, let's say this is positive terminal and this is negative terminal, then when there is no current flowing, from this battery, then in that case the potential difference across these two ends, this is, let's say, A end, this is B end, then VA minus VB is equal to the EMF when there is no current flowing through this, means when I is equal to 0, the potential difference across this cell is equal to E, means the V is equal to E when there is no current flowing. Now in case of this, the simply the EMF between A and B, this whole system can be replaced by a single cell, which is let's say of E effective EMF and R effective internal resistance. This whole can be replaced by this single cell EAB, which can be written as E effective. This is given by E1 plus E2 plus dot 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 plus En, and the resistance effective can be given by resistance internal resistance effective can be given by R1 plus R2 plus R3 plus dot 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 plus Rn. Now what one important thing to note here is, if I have to take a direction of EMF here, let direction means the cell can be connected in this way or in this way. The cell can be added here in both of these ways. So I have to take one direction of cell as positive. Let's say I am taking this side as of higher potential. Then if this is positive, this is negative terminal of the cell, I will take its EMF as positive in this calculation. So if I am writing the E effective here, then if it is I am taking from this side to this side, then I have to take the higher potential here and let's say lower potential at this side. Then what I will do is or we can say that we have to take considered a direction of this arrangement of this cell as positive. Let's say I take this as positive in this arrangement, means if a cell is placed like this, then I will take its EMF as positive, and if it is placed like this, then I will take it as negative. I have to take one convention, and then it means let's take example for this. Let's say there is a cell here, there is cell here of E1, E2, E3. These are the magnitudes of EMFs, and I want to find the EMF between these 2 points. Then I will, let's say I take this as positive, then this will be also positive and this will be negative. So E effective between them will be E1 plus E2 minus E3. Means if this is in opposite order, this is connected in opposite manner, then it will be taken as negative. And if I take it as negative, this is negative, this will become negative, and this will become positive. So I will write it as negative, negative and positive. And for the EMF, I will have to take the magnitude of this whole, because some can be positive or negative, but the EMF we have to use should be what we say positive value. We are talking about the magnitude of EMF. For this we have to take this magnitude modulus, and that's it. That's how we will calculate the EMFs. In this case I haven't shown the cell because the arrangement can be any type. And in case of parallel connection, let's say there is a cell here of E1 EMF and R1 internal resistance, then another cell, and dot dot dot. This is final cell here. These all are connected together with each other in any circuit, and this is R2, E2, E3, R3, and this is En, Rn. So this whole system can be replaced by, this whole combination can be replaced by a single cell with E EMF and R effective internal resistance, and the E effective will be given as, for this case we have to first calculate the R effective, which is given by 1 upon R effective is equal to reciprocals is equal to 1 upon R1 plus 1 upon R2 plus dot 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 plus 1 upon R. So first we have to take the effective resistance between them, and then we have to calculate the E effective, which we can do by simply E effective upon R effective is equal to E1 upon R1 plus E2 upon R2 plus dot 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 plus En upon Rn. Now one important thing here is that if similarly like in this case I have to take one sign, one arrangement as positive and other arrangement as negative. Means if the cell are, let's take an example for this. Let's say there is a cell here, there are 3 cells, they are arrayed like this. Then the EMF of this cell in this equation, let's say this is E1, this is E2 and this is E3. Then the EMF, let's say this arrangement I am taking as positive, then this will be positive, this will be positive. So I have to take all the EMFs in this equation as positive, and if this is reversed, then I will have to take this EMF with a negative sign here, and if this is reversed, then I will have to take this E3 as with negative sign, and if I take this as negative, this arrangement as negative, then this will become positive. So that's it. I have to take the sign of this EMF according to the arrangement of the cell, and resistance, it will always be positive. Now one more thing is, if I want to know the sign of the cell, let's say there is some combination of cells and I want to know that I have taken the magnitude of E1 plus E2 plus E3. This is a series connection. I have taken the magnitude of all these to tell the EMF, but I don't know if the effective cell I have made, it will look like this or it will look like this. I know the magnitude, but I don't know how it will look like. So for this I have to remove this modulus sign. Then to know the sign of this resultant cell, effective cell, we just have to remove the modulus sign from here, and let's say I have taken this arrangement as positive. Then if the sum of all these values becomes negative, then it means the effective cell of this I will get would be negative of this arrangement, which means the cell will look like this and its magnitude would be equal to the magnitude of this. And if I take this arrangement as positive, then if I take this arrangement as positive and this value turns out to be, let's say, positive, then the resultant cell will look like this, same as the arrangement I have chosen. This is A end, this is B end, this is A end, and this is B end. If I have taken this arrangement as positive and the sum of all this EMF turns out to be positive, then the resultant cell will also be of the same arrangement. If the sum becomes negative, then the arrangement of the cell will become opposite, means this way. And if I depends on what arrangement I have chosen. If the sum is negative, then the arrangement will be in opposite way in the resultant cell, and if the sum is positive, then the arrangement which I have chosen will also come in here, and if I choose this, then it will become this. Same as simple. Similarly, this will happen in this case of parallel addition. Now next thing is, let's say there is a cell here, it has EMF E, internal resistance R, and there is a resistor connected to it with R resistance. In this simple circuit, let's say there is some current flowing. This is a battery and there is some current flowing through this, and the current flowing is, let's say, I. Then the potential across this resistor would be equal to IR. So this is A point, this is B point, so VAB, the magnitude of VAB would be equal to IR, where I is the magnitude of current, R is the resistance across this resistor. So the resistance voltage across this resistor is VAB, and this voltage should be same as the potential across CD. So VCD should be equal to VAB. Now if the current is flowing in this direction, then the potential of P should be higher than VA. Means current flows from higher to lower potential. It means VB minus VA is equal to VB minus VA is equal to the current in this direction I into R. And potential here at D would be equal to VB, and potential at here C would be equal to VA. There is no resistance here, so the current will be same as here. And since the potential difference across this cell is V and the EMF of the cell is E, in actual this E is equal to the total, we can say the V is equal to IR, and this EMF is equal to this IR plus this RI. Here this is called V, potential difference across the cell, and this is the potential drop in the cell. This is the potential drop in the cell, RI. Now the EMF of the cell is the sum of these two, or we can say the potential difference across the cell would be equal to E minus IR. When there is I current flowing through the cell, if there is a cell with internal resistance R and EMF E, then the potential difference between two ends V would be equal to E minus the current passing through it is I, then it would be IR, the potential difference across this cell. And this can, how can this be said, the EMF is due to, okay, let's not go in details, just remember this. Now one more thing about current is that in case of semiconductor, the current is due to the electrons and the holes. Holes and electrons both provide current in the semiconductor. We have to add the current of both to give the total current. So the current is given by NEA VD, which is the drift velocity, of electron, plus NE, the charge of hole, the Q of hole, the charge magnitude of the hole is also equal to the charge magnitude of the electron, which is both have the same magnitude of charge, so both will have E electron charge. And let's say the density of electron is, let's say, Ne, and let's say the density of hole is NH, and its charge is again E, and area of cross section would be same for both. In this cross section, let's say the density of electron is N, the density of hole is H, and the area of cross section is A, and Vd is the drift velocity of electron and Vdh is the drift velocity of holes. Then the current will be given by this, which can be written as A E bracket Vd can be written as E times mu of E, mobility of electron times density of electron plus mobility of hole plus multiplied by density of density of holes, number density of holes. So this is how we can give the current in the semiconductor when there are holes also present. And next topic would be, the next topic is potentiometer. Let's first talk about Kirchhoff's circuital law and some tricks for resistance. In case of resistance calculation, there is some symmetry. Let's say there are two types of special cases in case of resistance. Let's say there is A and this is B. The circuit is like, we will take an example for understanding it. Let's say there is a resistor here R and there is a resistor, let's say R1. There is another resistor, let's say R2, and this is R4, this is also R4. So when, let's say this point is C, the resistors between A to B can be given by the resistance from A to C and C to B. So RAB is equal to RAC plus RCB. The resistance between C to B can be given by, let's say this line, I am drawing this line, and this whole setup is symmetrical about this line. It means there is symmetrical about this is symmetrical about the CB line, which is the path along the resistance. Then we can do it, what we can do is we can flip this and merge them, or we can say add them parallelly. So what would happen is that this will get added parallelly to this will get added parallelly to this, and this will get added parallelly to this. So this will give this C to B arrangement look like this both, sorry, what is this? This is R1, this is R1, this is R1, this is R2, this is also R2. So this is symmetrical now, R2, R2, R3, R3, R4, R4. These are symmetrical about this axis, so I can flip them and merge. So R2, R2 when I add parallel will give R by 2, and this will give R3 by 2, and this will give R4 by 2. So this circuit from this can be simply converted to this, and now it can be added like this. Now I can take another case. Let's say there is a point here. This is a resistance R1. This is another resistance R1. This is the first case I am talking about. This is let's say R2. This is R2. This is R3. This is R4, this is R3, this is R4, and this is R5, this is R6, and these are headed by this is R7, this is R also 7. So if we see along this AB line, we will see that if I divide this register into two parts, if I divide this register in R5 into two parts, I will get R5 by 2 here, R5 by 2 here, and dividing this R6, we will get R6 by 2 here and R6 by 2 at this side. So joining from this mid part, अमित इस पिछले वाले पार्ट को एडिट कर देंगे, ये वाले पार्ट को रिमूव कर देंगे. Start. Now let's take another example for this, which is more complicated. Let's say this is A end and this is B end. There is a resistor here. Let's say this is R1 and another resistor here, R1. It is connected by a resistor R5, and there is a resistor, let's say R1, this is R2, this is again R2, this is R3, and this is, let's say this is R3, this is R4. Now what we can do here is that we see that this thing looks symmetrical about this line R3, R2, R1, and this part can also be made symmetrical just by dividing it into parts. Let's say like this becomes R5 by 2, this becomes R5 by 2, this becomes R4 half, and this becomes R4 half. Now this becomes symmetrical about this line, but I can merge it by flipping it. This is mirror symmetry, symmetrical about this AB line. Now I can simply merge them. I can merge this and this will start looking like this will get added to this, 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 and this will get added to this, all parallelly added. So this will be R1 by 2, this will be R2 by 2, and this will be R5 by 4, and this will be R4 by 4, and this would be R3 by 2. This is B point. So we can see that this part of the resistance, it is not connected in the series, it is just free, it is not the part of the circuit anymore. It is only its one end, it's part of the circuit, so it is useless. These two resistance are useless. I can just remove them and find the resistance due to this R1 by 2, R2 by 2 and R3 by 2. So the resistance would be the sum of R1 plus R2 plus R3 by 2. This will be the total resistance. Now if I add another resistance here, let's say this is, let's say R6, this is, let's say R7, this is, let's say R8. Then in that case there would be a R6 resistor here. Since nothing is added parallel to it, R6, it will remain same. This will remain same R7, and this will remain same R8. Now this whole circuit will start looking like this. And now it is hard to tell how to calculate this circuit, but okay, we have simplified this as this much. Moving ahead is tough. Now what else we can do here? Now see, what happens is that here we have to look at the current for understanding what is going on in the circuit and how do we get these flows. Let's say there is an end A and there is an end B. There is a resistor here, one more here, and it is connected like this. This is R1, this is R1, this is R2, and this is R2, and this is R3. So what happens is that this is symmetrical about this line. This whole setup is symmetrical about this line. So we can say that if I1 current is flowing in this direction, then I1 current will be flowing in this direction because these are symmetrical about this line. And if I2 current is flowing in this, then I2 current is also flowing this. And we know that the total current flowing through this and the total current flowing through this, they will give the total sum equal to I. The total I is equal to I1 plus I2, I1 both I1, this will give equal to I, and in this case this will be equal to I2 plus I2. It means that the whole current is passing through this and no current is passing through this resistor. So when there is a symmetry like this, when the circuit is symmetrical about the line joining these 2 points, then this part can be rejected. Like this resistor part can be rejected. Like if I add many resistors here, many resistors here, let's say R3, R4, R5, many resistors I have added here, all of them will be discarded because there is no current going into this. So I can discard it and the circuit will become this simplified. Or I can, and after this, so I can discard this current in this circuit, and after this, since I know that the current in this and in this both are same, and when adding them parallelly, I will find out that I can also draw this as RA1 and R1 merged to it. Both R1 resistors here and both R2 resistors here parallelly, and this is B. I can also draw this circuit like this, means I am merging these 2 resistors and these 2 resistors, and it will give me this circuit, which means R1 by 2 and then R2 by 2. This is B end, this is A end. And nothing else. As simple as that. When the current in the circuit or the resistors in the circuit are symmetrical about this line, then I can ignore this resistance. That's it. Now moving to the Kirchhoff's circuit law. KCL. In KCL, the first thing we study is that the total current going in is equal to the total current going out, and the summation of all the current at any point at any point would be equal to 0. Let's say at any junction, let's say some I1 current is going inside, I2 current is going inside this at this junction point, and some I3 current is going outward. Then the I1 plus I2 would be equal to I3, or I can say that I1 is going in, I2 is going in, and I3 is going out, so it will be taken as negative sign. Sum of all this current would be equal to this. We have to consider the direction, we have to consider the sign of the current we will choose. Let's say if it is ingoing, if ingoing is positive, then outgoing is negative. So I3 was going out, it was taken as negative. If outgoing is positive, then ingoing will become negative. Now this is because the accumulation of charge cannot happen, so the total charge passing through this point should be equal to the total charge. Total charge coming to this point would be equal to the total charge coming out of this point, away from this point. And second thing is the potential, delta potential across a loop is equal to 0. Means if there is a circuit like this and there are some elements in the circuit, I don't know what are they, but if I take any point here A and any point and I move through the circuit and add all the potentials, if I take the sum of all the potentials drops of the circuit over the loop, then I will find that the total potential drop of all the circuit will be 0, because this will become VA minus VA, so this will become 0. So I can say that yes, integration of dV over the closed loop would be equal to 0. I can write it like that. And how to apply this? In case of a simple circuit, for example, there is a battery, there is some resistance R, current flows I. Then in this case, we will take this, the potential difference across this point here. Let's say it is point A, it is point B. The potential difference, let's say it is point C, and it is T. Then starting from the C point, there is no potential change from this end to this end. This is VC, and now this is the potential drop from A to B, changes from A to B. So we will take VB minus VA added to this VC, and then the potential changes from, the potential remains B here, and now we will pass through this cell and we will get the potential difference here. In this case is VC minus VD. We started from VC, then the change was VA, VB minus VA was the change which we added, and then VC minus VD, I guess. What happens is that is the total potential at this point after we have moved through this loop. So the potential at this point, again at this point, is VC cancels this VA, both are equal in potential, and VB cancels VD, both are equal in potential, so it will give 0. We can say that this was the potential, sorry, this was not the potential. We have to take the sum of all potential differences only, not the potential values. So first potential difference is this, and then second is this. Or if I come across the loop, I will get the VC back. I will get the VC value back if I add VC here. And if I only add the change of potentials, change of potential here and here, it will give 0. And in this case the VB minus VA, this is a lower potential, this is a higher potential, so this is a negative value IR, and this cell is potential difference. So since the current is flowing in this direction and the potential I have taken in this direction, the potential drop I am taking along this direction, or this is the final potential and this is the initial potential. So if I am taking the loop, if I am considering the potential difference across in this manner, in this clockwise manner, then we will get VC minus VD here and VB minus VA here. But we know that the potential drop across any two point, if there is any current flowing, if there is current flowing IR, then the potential drop across this point from final minus initial, this VB minus VA would be equal to minus of IR. How can I say that? Because I know that current flows from higher potential to lower potential. So if current is flowing in this direction, then this would be higher and this would be lower, so this value will be negative. And since current is only positive taken, so I have to take a negative sign. So when I write the potential difference, so if there is a point, let's say A, and there is a point B here, and there is some current flowing in this direction, and this direction some current is flowing, then VB minus VA, if I want to write, I will write it as minus IR. If I want to write the V final minus V initial, like the potential I am taking, potential difference I am taking along the same direction as the current, then I have to take a negative sign with this value, because the current would be flowing from higher to lower, not lower to higher. So this is an important thing we have to take care of, that if potential drop is taken in this manner, then the direction of current will be taken as positive in this manner, and negative means if the current is flowing in this direction, then it will come with negative value, and if the current is flowing in this manner, opposite manner, if the current is flowing in this opposite manner, then it will be taken as positive value. So let's take another example. Let's say there is a cell 8 volt, this is a cell 3 volt, this is a resistant here, let's say 2 ohm, and it's connected like this. So what happens is that, first of all, we say that there is some I current from this. Let's assume that this is moving in this direction, assuming it, so current will be flowing like this. Let's say I am taking the potential drop in this manner, so V final minus V initial, in this manner if I go, then this is negative side and this is positive side, so this will give minus 8 volt, this will give final minus initial give 3 volt, and this is IR, current is flowing in this direction. So and this current direction is in opposite direction of this, so I will take plus 2 ohm into I, since I know that this is, let's say, VB and this is VA, I have to take the VB minus VA. So to take the VB minus VA, I have to take the current flowing from in this direction IR. Since the current is flowing in this direction, I will take, if the current was flowing in this direction, I will take a negative sign, but it is already flowing in the opposite direction of this, so this is already negative value, so it will be taken as positive. Means if the current is flowing in the same direction as the considered direction of potential drop, then it will be taken with negative sign, but if it is flowing in the opposite direction, it will be taken as positive. This will be 0 according to the Kirchhoff's circuit law. All the potential drops are taken, and this gives 5 volt is equal to 2I. So it means there would be a current flowing in this direction, this manner. I is equal to 5 by 2 ampere in this manner. My assumption was correct, but if I take the current to be flowing in this direction, then I have to take a negative sign here because it is flowing the same direction is considered. Then in this case, this we will get this, minus I will become this. So it means the direction of the current I have taken is opposite, so the actual current is flowing in this direction. This is what this negative sign will tell. So that's the Kirchhoff's circuit law. And some tricks about circuits. Let's say we have 2 loops. It is resistance, let's say R1, it is, let's say, resistance R2. This is a V1 potential and this is a V2 potential. These are circuit. This is a circuit connected like this. Then in such a circuit, what I can do this is that first I have to see that I can simplify this circuit. I can simplify this circuit by doing what? This I have to first see that this resistance is the part of this loop. This is loop 1, this is loop 2. This resistance is the part of this loop. This resistance and this all three are the part of this loop 1. So I have to make sure that the resistors which are part of the loop should not become part of any other loop, or when I can shift this resistor, but in such a manner that this will remain the part of the same loop, and if it is a part of any other loop also, then it should be remain part of the other loop too. So I can write it as R1 plus R3, this resistance R2, and this is V1 and this is V2. Now what is important here is that I cannot shift this resistance here or here, because if I shift this resistor here, this will become part of this only but not this. But we know that this is a part of this loop also, so it should be part of both loops, loop 1 and loop 2. So I can simplify that much in this circuit. Now this was the first thing about simplifying the circuit. Now I can take the nodal analysis. Let's say this is 8 volt. Let's say this is 8 volt and this is 5 volt. Now what I can do is that this 8 volt can be written as, let's say, some Y potential here and X potential here. This is X potential here and Y potential here. So X minus Y is equal to 8 volt. Similarly here I can take, since this line there is no resistor between them, there is no component between them, so the potential here should be equal to the potential here, because if there is some potential difference between them, there should be some resistor also, otherwise there would be infinite current flowing between them if their potential is not same. So their potential should be same if there is no resistor between them. If there is no capacitor, resistor or inductor between 2 points, let's say these are the 2 points A and B, and they are simply connected by a zero resistance wire, then the potential at A should be equal to potential at B. This is the second point, 2 points here, and therefore this would be Y at Y potential, and let's say this is at Z potential. Z minus Y should be equal to 5 volt. Now what I can do is that the current from this point to this point can be written as X minus Z, that is the potential difference between these two. That would be equal to, let's say the current through this is I1, through this let's say it is I2. Then I will say that I1 times R1 plus R3. This would be equal to the potential difference between X minus Z. I can use this, and the current I2 can be given as, I have to, since the potential here is Z, the potential here should also be Z, and if the potential here is Z and the potential here is 1, then I can say that I2 into I2 is equal to Z minus Y. Higher potential minus lower potential will give the current in this direction. This is how I can solve. Now let's say I can take any value of Y. I can, let's say, take 0 here, 0 here, and then this will become 5 and this will become 8. And if I take, so this will give 8 minus 5, which is 3. So I1 will become 3 over R1 plus R3, and this I2 will become Z minus Y, which is Z minus Y, this is 5 divided by R2. 5 minus 0 is 5 by R2. Now if I take this Y instead of 0, I can take it as, let's say, minus 8. Then to balance this potential difference, there would be some minus 3 potential difference here, 0 potential difference here, so that 0 minus 8 is 8, and minus 3 minus 8 will become 5. So now what I do is X minus Z. X is 0, Z is minus 3, so X minus 3 is again 3, again the value is same, and Z minus Y, which is minus 3 minus 8 is 5, so again the value will remain same. So this is called nodal analysis, where we take any point, or we call it node, and fix some potential to it. And we should be careful about when fixing the potential, that if the 2 points are connected by 0 resistance wire, then there would be 0 potential difference between them. And I can now remove this setup cell, and this system will look simply like this if I remove this. Now it is easy to calculate from this potential difference. I can calculate this current. From this potential difference, I can calculate this current. Okay, this was nodal analysis. Now taking another example in case of nodal analysis. Let's say this is the question here. Question is given like, there is a cell here with 2 volt. This is a 10 ohm resistance, again 10 ohm resistance, again here 20 ohm resistance, and then a cell of 4 volt potential difference. Here it is 10 ohm resistance and connected to this. Now we want to solve it. We can solve it by 2 ways. this is 10 ohms, this is 4 volt. We can solve this question in two ways. One method is Kirchhoff's circuital law. I have to make loops and assume that there is some current, let's say I1 flowing through this, and it divides into, let's say, I2 and I3, and this passes through this, I2 passes through this, and it gets added here, and I1 current passes through this area. So using this Kirchhoff's circuital law, I can just make the equation of the potential difference across the loops. Like the potential difference across this whole circuit would be 0, and through this will be 0. I can get, let's say, value, let's calculate it by this method. So if I am taking the potential drop, if I'm taking potential in this loop in this clockwise manner, then I will say the potential drop is 2 volt. The current is in the same direction as the clockwise way, so I will take minus I1 into 10. Then it is also in the same way, I will take it as minus 20 into I3, and this is minus, this is connected in this manner, so its potential drop is minus 4 volt, and this current is flowing in this direction again, so this is minus 10I. This is equal to 0. This is the first equation we get. Simplifying it, we get, so it is becomes 20 I1 plus 20 I3 is equal to minus 2. This gives this equation, and one equation we have is that I1 is equal to I2 plus I3. I1 is equal to I2 plus I3 from the junction rule, and from this loop we can make another equation. Let's say I am taking the loop in this manner, so the potential drop here would be 4. Going from this to this point, the potential drop is 4 volt. Then going from this to this and across this resistor, the current is in opposite direction of the considered, so it will be taken as positive 10 into I2. And then going from this to this across this resistor, this would be minus 20 I3, because it is in the same direction of this clockwise manner, anti-clockwise manner. Now this will have negative 4 volt. Now going this way, we had started from this point and now going to back to this way. This is moving in the opposite direction, so I will take minus, so plus I2 into 10. This would be equal to 0. It will give 20 I2 minus 20 I3 is equal to 0. There, sorry, is it right? Okay, this was 4 volt. So we get the relation that I2 is equal to I3. I2 is equal to I3. Since I2 is equal to I3, I can say that I is equal to 2I2 or 2I3. So in this equation, if I put the value of I3 to be, if I put the value of I2 to be 2I3, then we will get this equal to 60 I3. And the value of I3 will become minus 2 over 60, which is minus 1 over 30 ampere. So the I3 is actually flowing in this direction. We were thinking that it is flowing in this direction, but the value we got for I is negative. So the I3 is flowing in this direction, and the same magnitude of current is flowing in this direction. And the I1 current, which is the 2 times of this, it is flowing again in this direction. Since I3 is negative, all of them become opposite, so the current is flowing like this, in this manner, from this to this and like this way. Now So current goes like this. This is I3, this is also equal to I3, this is also equal to I3, this is also equal to I3, and this is I1, this is I1, which is equal to 2I3. Now we can also solve this question using nodal analysis. Without using Kirchhoff's circuit law, I can solve this using nodal analysis. Now to solve this question using nodal analysis, what we can do is that first take some points here. Let's say this is A, this is B, this is C, this is D, this is E, this is F, let's say this is G. Now there are two loops, this is loop 1 and this is loop 2. So what we have to do is that I first have to simplify this circuit. Simplifying in such a way, I have to shift the resistors to make this look simple. Let's say there is I1 current going this way, I2 here and I3 here. So to simplify the circuit, I can shift this resistor, let's say here. This resistor is part of this loop and not this loop, so I can move this resistor anywhere in this circuit. I can move this resistor in this circuit, in this loop, such that this, but I cannot place this resistor here, because if I place this resistor here in this part, this will become part of this loop. Since it is not part of this loop, it should not become part of this loop after I shift. So if a resistor is part of some loops L1, L2, L3, then I have to shift the resistor in such a way that it remains the part of those loops and does not become part of any other loop. So if this resistor was part of this loop, I can shift it here 10 ohm, and this will remain the part of this loop again and not the part of any other loop. And similarly, this is the part of this loop, this resistor is the part of both loop, so it should remain the part of both loop. So I will not shift this, I can shift this. This is the part of this loop, so I can shift this resistor here. Again, there is 10 ohm resistor here again. This was part of this loop, so again this is part of this loop. I have just shifted it here. Now this whole can be written as 20 ohm, and this will become 20 ohm. Now this becomes simple, and the potential at VB equal to VC and equal to VD. Now if I want to solve this using nodal analysis, let's say there is some potential at this end X, then there would be some potential at this side Y. This will be same here, Y, Y, Y. This potential would be remain here Y. This would be same everywhere here Y, because there is no resistor here. Now what I have to do is that this, I can write the potential here as W and the potential at this side as Z, such that X minus Y is equal to the potential difference, which is 2 volt, Z minus Y is 4 volt, W minus Y is again 4 volt. So this gives Z is equal to W, Z becomes equal to W, and let's take any value of Y. I am taking Y is equal to 0, so this will be 0 potential here, 0 potential here, 0 potential here, and the X becomes 2, this becomes 2, this becomes 4, and I can remove the cell now. Now I can remove the cell, and here this will become 8 volt, this is 8 volt, this is 2 volt, and I can now remove the cell. Now I removed all the cells, and put the potentials. It is over at zero potential, useless. This part becomes useless. Now I can calculate. In the previous case I had found that I3 was equal to minus 1 by 30 ampere. Now in this case we will calculate the potential difference from, let's say the current flow is I1, so I will get 4. The potential drop from this, let's say this is G point and this is AB, let's say D point. So the potential difference between these two is, let's say 4 minus 2. I am taking the potential drop in this direction. So this is the final, this is the initial, or let's say this, I am taking this part of the loop. This is D, this is A, D is at 4, this is at 2 volt, and this is the circuit with I1 current flowing through it with 20 ohm resistance, and there is some I2 resistor with I2 current flowing this resistor and 20 ohm resistor. Now if I take a loop here, let's say loop in this manner, then the potential of this minus this, let's say I start from this point, so 2 minus 4, which is minus 2 volt, plus this current is flowing in this direction, so I will take a negative I1 into 20, negative of I2 into 20, that is equal to 0. So it gives I1 plus I2 is equal to 2 upon 20 minus, and in case of this I3, we again get some same equation. We again get the same equation. In case of I3, we get I1 plus I3 is equal to minus 2 over 20. Because both circuits are looking similar, when we make the equation for this loop, we will get the same equation again. And now since we know that I1 is equal to I2 plus I3, we will get that we can eliminate this value, subtracting this from this over here. Right. Taking the sum of these two, I will get 2i plus I2 plus I3, which is again I, is equal to, the sum of these two will be minus 1 by 20. So minus 1 by 10, minus 1 by 10. This will become 3 I1 is equal to minus 1 by 20, which gives I1 is equal to minus 1 by 16. Something like that. Or if I am forgetting something, well, this is the method how to solve this. Maybe I am doing some mistake, recheck it if there is any mistake in calculations.